section is on logarithmic functions, which are related to exponential functions, you'll see in just a minute. So if you will look at the top of your notes, you'll see explore logarithmic functions, and it says consider the exponential function some y equals some base raised to the x power. Remember, an exponential function is one where the x is the exponent. So if we wanted to know what the inverse of that was, if you'll think back to a couple sections on inverse function, the first thing that we do with the inverse function is we switch the x and the y. So we would say x equals a to the y, and then we would solve it for y. But the problem is there's no algebraic way to solve for y when it sits up there in exponent land. So we have a problem. So how can we get to that inverse function? What we have to do is we define a new function, and we say that when this is really what the inverse should be, when you start with y equals a to the x, that we solve by y by saying y is equal to the log base a of x. And I know you don't really know what that means yet, but just hang with me. This is the definition of a logarithmic function. So it's a logarithmic function to the base a. So the base, this is the base, this is the exponent. The base goes here. It's the log base a of x, and it's equal to y. Notice the y was the exponent. So these two are inverses of each other. Here we see that a must be greater than 0, and a cannot equal 1. Remember that from when we did exponential functions, and we talked about that and the reason why. And it's so we define a logarithmic function as y equals log base a of x if and only if, that's what IFF means, x equals a to the y. So you can go back and forth between the logarithmic function and the exponential function. The domain of the logarithmic function is that x must be greater than 0. So you need to see where the star is in your notes. You need to memorize this. A base raised to an exponent equals some number, and it's the same thing as saying, so these two things are equivalent, the exponent is equal to the log of the base to the base of that number. This side, the left-hand side, this part is like you are the base and you're kind of on the ground looking up at the exponent, whereas this side over here, this is kind of a weird way to describe it, it's as if you're the exponent and the exponent is on the ground, so to speak. You'll understand that more when we do some. So, for example, that A example, it says if y equals log base 3 of x, then we can rewrite that as saying x equals 3 to the y. Those are the same things. So here's the base. Here's the What we're taking the log of becomes the so-called answer, and the answer here becomes the exponent. So you're going to just again have to memorize that. Here's another one. Y equals log base 5 of x means, so if that's true, then x equals 5 to the y. And a good way to memorize that is to put some numbers in. So if we know that, I'm going to do it right underneath here, 8 equals 2 cubed. That is true. Okay, then working backwards, then I would know that 3 is equal to the log base 2 of 8. Those two things are equivalent, and that's the way when I was learning these as a student, I memorized them with that very one. 8 equals 2 cubed is the same thing as 3 equals log base 2 of 8, and you just have to understand where they go. when you go back and forth. So let's look at example 1a. It says change each exponential expression to an equivalent expression using a logarithm. So we've got 1.2 to the third power equals m. So I always think of the base first, the 1.2. So I'm going to be taking the log of the base. Okay, log in base 1.2 of what was the answer is the exponent becomes the important piece here, the answer in the log expression. Those mean the same thing. Let's look at b. E to the b equals 9. We can say again, what is our base? So log base e of what was our answer equals our exponent, which is now our answer. And we're going to learn about log of e, a different way to write that later. All right, let's look at c. A to the fourth equals 24. Think about the base. The base is a, so log of a, base a of 24 equals, the answer should be the exponent. The exponent is the important piece here. So that's going that direction. Now let's go the other direction. This time, in example 2, I'm going to give you the log, and you write the equivalent exponential expression. And again, I always start with the base. The base is a. Raised to what power? Remember, the exponent was the answer, so a to the fifth equals 4. Those two are equivalent expressions. So log base e of b equals -3. What's the base? E to the -3 equals b. The answer in a log expression is always the exponent. And finally, c, we have log base 3 of 5 equals c. Our base is 3 raised to the c power equals 5. Okay, now how do we use that and what does it really mean? So let's look at example 3a. It says find the exact value of log base 2 of 16. Well, what we're going to do is we're going to say log base 2 of 16 is equal to some value we call y. Now I'm going to rewrite that as an exponential expression. So the base is 2 raised to the exponent equals 16. And we learned back in the last section on exponential expressions that we need to get exponential equations, we need to get both sides with the same base. So is 16 a power of 2? Yes, it is. So 2 to the y equals 2 to the fourth. Therefore, since the bases are the same, y equals 4. So we can use what we know about exponentials and their relationship to logs to solve for exact values. Let's look at b. Log base 3 of 1/27, and again we're going to say equals some y, so let's rewrite it as an exponential. 3 to what power? The y equals 1/27. Now this one is a little tricky. Is 1/27 the power of 3? Yes, it is, but notice it's a reciprocal of a power of 3. I'm going to go over here. 3 to the third power is 27, so 3 to the -3rd power is 1/27. So we're going to go say 3 to the y equals 3 to the -3rd. Since the bases are the same, y equals -3. All right. Okay, so let's look on the back. It says, as with all inverse functions, the domain of the log function is the same as the range of the exponential. So here we have the log, here we have the exponential. The domain of the log is the same as the range of the exponential, which is 0 to infinity. Remember, up here we said x must be greater than 0. So the domain of the log is 0 to infinity, and the range of the log is the same as the domain of an exponential, which, if you'll remember, is negative infinity to infinity. So the range of the log is the same thing. And this is true for all inverse functions, which you learned again in a couple sections back. Inverse functions. So that can help us. So let's look at example 4. It says find the domain of each logarithmic function. So here's what we have. F of x equals log base 2 of x plus 3. Remember, f of x is the same thing as y. So what that means is I can write that as an exponential, the base raised to the exponent y equals x plus 3. So x plus 3 must be greater than 0. X plus 3 must be greater than 0. And x must be greater than negative 3. So this must be greater than 0. Because we're looking here at the range of the exponential, the y part must be greater than 0. All right, let's look at B. We have g of x equals the log base 5 of 1 plus x over 1 minus x. We're going to say that's the same as y. What that means is take your base, raise it to the y, equals 1 plus x over 1 minus x, but we know some things here. We know that this whole value must be greater than 0, which means that the numerator must be greater than 0. So x must be greater than negative 1, but also because of the denominator, we know that 1 minus x must be greater than 1, or 1 must be greater than x, which means that x must be less than 1. But we also know, because of domain restrictions, x cannot be equal to 1. So wow, what is the domain here? So the domain of that logarithmic function, remember, is the same thing as the range of the exponential, and the range of the exponential is what we just wrote here. So it has to be greater than negative 1 but less than 1. So it's between negative 1 and 1, or you can write it like this, negative 1, like that. That is the domain of the log. Now let's look at C. It's a little tricky. We have h of x equals log base 1/2 of the absolute value of x. We're going to say that that's equal to y, and that means, let's write it as the exponential, the base to the y equals absolute value of x. But the absolute value of x, we know that this must be greater than 0. Well, how is that greater than 0? The value of it, not what's inside, but the whole value, the absolute value. Think about if it was negative 4. Absolute value of negative 4 is 4, so that's greater than 0, right? So what's the only thing absolute value of x can't be? Absolute value of x can't be 0. We can't have x be a 0, because then we would have 0 as our answer, and it can't be, it has to be greater than. So this one's tricky. So the domain is negative infinity to 0, not including 0, union 0 to infinity. Because any negative number you put in there, once you take the absolute value, it will be greater than 0. So that one was kind of a tricky one for the domain. All right, let's take a look at graphing logarithmic functions. It says, since exponential functions and logarithmic functions are inverses of each other, the graph of the function y equals log a of x is the reflection across the line y equals x of the graph of y equals a to the x. So what we're going to do here is we're going to graph the log function, the exponential function, and the function y equals x on the same coordinate plane. We're going to do it twice. We're going to do once with a equal to 2 and once with a equal to 1/2. So let's draw a set of axes here, our x and our y, and we're first going to say a is equal to 2, for example, meaning we're doing a is greater than 1. And if you'll remember, the exponential looked like this. We spent a lot of time with that, and we know that it goes through the point 0, 1. It also goes through some point, since a is 2, we have the point 1a. In this case, it would be 1, 2. Okay, I'm going to write that right underneath it. If x is 1, then y would be 2. Okay, so it would be 2 to the first, so y would be 2. And we also know over here it goes through the point negative 1, 1 over a. Now let me show you that with a being 2. That if x is negative 1, we would have 2 to the negative 1, which is 1/2, which is 1 over a. So those are the points that are on the exponential function when a is greater than 1, and in particular in this case when a is 2. The line y equals x looks like this. This is the line y equals x. 1, 1, 2, 2, 3, 3, etc. Okay? So the exponential function is going to be the reflection, meaning, this is really actually quite easy. We're going to take these points, 1a, 0, 1, and negative 1, 1 over a, and we're going to just rewrite them. So we would have the point, instead of 0, 1, we would have the point 1, 0, which is right here. That's the point 1, 0. Instead of the point 1a, we would have the point a, 1. Well, remember in our case a was 2, so 1, 2, 1. That's the point a1. I'm just reversing what we had. And then instead of the point negative 1, 1 over a, we have the point 1 over a, negative 1. And with it being 2, it would be 1/2 negative 1. So this is the point 1 over a, negative 1. And when I connect those, you can see that that log line is a reflection of the exponential. So this is y equals a to the x. This is y equals log base a of x. And I didn't draw, mine don't really look like that. They don't really look symmetric, but they really are if I had plotted the points more carefully. So let's do this again, only this time, let's say that our a is between 0 and 1, meaning that it's a fraction, and we're going to use a equals 1/2 as our example. So if you remember from exponentials, it would still go through that point 0, 1, but it would have been flipped across the y-axis. And it would have looked like that. Here is the line y equals x. So this was the line y equals a to the x, so 1/2 to the some power. And now let's look at some points on that exponential line. On this line, we would still have the point negative 1, 1 over a, negative 1, 1 over a, but think about what 1 over a looks like. I'm going to do it over here when a is 1/2. So it would be negative 1. If x was negative 1, then you would have 1 over 1/2, which is the same thing as negative 1, 2. Okay? We also still have the point 1a, just like we did here. On our exponential, we had the point 1a. So we still have the point 1a, only now our a is 1/2. So we have the point 1, 1/2. Forget that right there. 1a. Okay, so now I got to flip that to show its mirror image across that line. So I still, instead of 0, 1, I have the point 1, 0. So it goes through this point, which is 1, 0. Instead of 1A, it goes through the point A, comma 1. Remember A was 1/2, so we would have this point. I don't have room to write it, but that's A1. And then instead of negative 1, 1 over A, we go through 1 over A, which would be the point 2, negative 1. So what this looks like is it looks something like that. And I didn't draw that quite right either. This is that line's supposed to go right there where they intersect. We'll practice doing this on a graphing calculator and you can see them more perfectly. This one is a harder one to graph and see that it's symmetric. This one is actually quite simple to see. So I'm going to do some summary down here. So I'm going to make a list here of the function, okay, and the points that we had on each of these. So the function that we had and the points that we had. All right? So, in general, we started out with an exponential function y equals a to the x. Our example, our specific one, was we let a be 2. So we would have y equals 2 to the x. What points did we have? Our set of points included the points 0, 1, 1, 2, and negative 1, 1/2. So 0, 1, 1a, negative 1, 1 over a. All right? So this was for the function y equals a to the x. I wish I had a different color on this ink, but we're going to do it again now for the logarithmic. So when we did the general function of the log, we had y equals log base a of x. Our specific example that we used was y equals log base 2 of x. And what points did we have? We had the exact opposite of the ones up there. Instead of 0, 1, we had 1, 0. Instead of 1, 2, we had 2, 1. Instead of negative 1, 1/2, we had 1/2, negative 1. Because these two functions are inverse functions to each other. All right? Over here, when our a was between 0 and 1, in other words, it was a fraction, I'm just going to do the example. We had y equals 1/2 to the x power, and the points that we had are still 0, 1, 1a, which is in this case is 1/2, didn't make it big enough here, and the point negative 1, 1 over 1/2, which is the point negative 1, 2. All right? When we changed that and we wrote as y equals log base 1/2 of x, in other words, when we wrote it, its inverse, our points were the reverse of those. So we had the point 1, 0, we had the point 1/2, 1, and we had the point 2, negative 1. So I hope you can see that there are two cases. Definitely this case, like I said, is easier to see. But you need to know that always you're going to have, with the exponential, you're going to have the points 0, 1, 1a, negative 1, 1 over a. And with the log, you're going to have the points 1, 0, a, 1, and 1 over a, negative 1. Even if a, it doesn't matter if a is greater than 1 or in between 0 and 1. This is always going to be true. It just takes some getting used to.